So last time, 2 weeks ago, 3 weeks ago, in fact, we discussed some deformation theory. And in particular, for K3 surfaces, we proved that for a K3 surface, there exists a smooth universal deformation and also we prove that all smooth deformations of a K3 surface are again K3 surfaces. So this first we discuss this, and then we define the period map so we considered a family of K3 surface over simply connected base. Simply connected. This is a family of K3 surfaces. And we defined a period map from base, from simply connected base to the period domain. A smooth 20-dimensional subset, complex subset. And also we proved so-called local Torelli theorem that tells you that if we consider a smooth universal deformation of a K3 surface, universal deformation, then the corresponding map from simply connected base to the period domain is local isomorphism. Okay, and today I want to define so-called global period map that is defined for marked K3 surface. So first of all, I would like to explain why for marked K3 surface we have a fine moduli space, not just moduli space, but even fine moduli space. So let me recall that marked K3 surface is a K3 surface with a fixed isomorphism of its second cohomologies with our favorite lattice, that is direct sum of U of 3 copies of U and 2 copies of E8 minus 1. So, so first part of today's lecture will be about the fine moduli space of marked K3 surfaces. So I will denote this moduli space in the following way. And first of all, as I said, this moduli space consists of all isomorphism classes of pairs X with phi, where X is a K3 surface, and phi is an isomorphism of its second cohomologous with integer coefficients, and lattice that is a direct sum of two copies of E8 so this is marking, and this is isomorphism of lattices. So what I claim is that if I fix this isomorphism, then there exists a fine moduli space of these pairs. I will explain why it's important to fix this isomorphism. But before, let me explain how to introduce the structure of a complex manifold on this set. So this is set of pairs, and we would like to how introduce the structure of a complex manifold on this set. So to do this, we will just glue universal deformations of K3 surfaces. So we glue the universal deformation spaces of the various K3 surfaces. So for any K3 surface, we consider the corresponding universal deformation. Then if we have a marking of the corresponding K3 surface with the lattice, then it induces canonically markings of all the fibers of S. And just because we know that locally this is something simply connected, so the corresponding local system is trivial. So if we fix a marking on the central fiber, and so the local system of the corresponding integer second cohomologous is trivial, so using this local system in this marking, we obtain markings on all fibers of the universal deformations, right? So from local Так. Ну что, началось развлечение с ранним. Я страшно скучаю по доске в 108 аудитории. Ладно. So from local parallel theorem, we know that the corresponding period map is injective. Hi. This is not all. Also, we know that this universal deformation from... А можно закрыть окно? Last time we discussed that the corresponding universal deformation is in fact universal for each of the fibers so the pairs deformation is 0 with marking can be glued along the intersection. The intersections. X0 in D. So one more time, what I claim. For a K3 surface, we have a universal smooth deformation. If we and this universal deformation is in fact universal for all fibers of S, of this universal deformation, right? We discussed this last time. Suppose we have a marking on the central fiber. Then this marking induces marking for all fibers of S. And this will still be a universal deformation. And now, from local Thoreau theorem, we obtain that the corresponding period map is injective. So, we can induce a structure of complex manifold on. So using these markings and using that all fibers of this deformation induce universal deformation for all the fibers, we can glue different deformation spaces for different K3 surface with marking into some smooth subvariety in D. Is this clear? Or so we glue them just along the corresponding intersection, okay? And obtain a structure of complex manifold on this set. Okay, so good. So the complex structures of the universal deformations for all K3 surfaces, for all marked K3 surfaces, define a global complex structure on this set of all isomorphism classes of pairs. And now let me explain why here we have a structure of fine moduli space. What does it mean to have a structure of fine moduli space? We discussed this.
We have a universal family?
Yes. Why we have a universal family on this set? Roughly speaking, to obtain a universal family on this set, we should glue the corresponding universal deformations. So we glued bases of these universal deformations, right? And now to obtain a universal family, we need to glue these universal deformations. And here we will use that marked K3 surface doesn't have non-trivial automorphisms. In the end of the lecture, I will try to explain very, very roughly why we can't even hope to have a fine moduli space for all K3 surfaces without marking. Roughly speaking, because K3 surfaces have automorphisms, non-trivial. And for marked K3 surface, we don't have non-trivial automorphisms. So because of this, we can glue universal deformations to obtain a universal family here. So first of all, let me explain what is so let me first explain why maybe a 0 phi doesn't have non-trivial automorphism. In fact, I hope that we will discuss this in the next lecture, that there is the following theorem, that if an automorphism of a K3 surface acts trivially on its second cohomology group, then the corresponding automorphism should be identity. So this theorem tells you that, of course, it will follow from Tarelli theorem, the theorem that automorphisms, non-trivial automorphisms of K3 surface acts non-trivially on its second cohomology group. Right? And what is an automorphism of the pair? An automorphism of the pair, it's not just an automorphism of S0. It should induce an automorphism of H2SZ with the markings. Yes, and all automorphisms induce some non-trivial automorphisms here, so it does not preserve marking. So if we fix marking, we doesn't have non-trivial automorphisms of K3 surfaces with markings. Okay? And what I want to explain today, very, very roughly, is that if some family of objects has non-trivial automorphism, then we can hope to have fine moduli space. Fine moduli space. It's a very, because in fact this is a very common idea in mathematics. If we have non-trivial automorphisms, then we cannot obtain a fine moduli space. To obtain a universal family, we should have trivial automorphisms. And in the case of K3 surface, to obtain trivial automorphisms, it's enough to fix marking. Okay? If we fix marking, then we can hope to construct some universal family on the corresponding moduli space. Okay. And now so I explained why here we can have fine moduli space, and now let me explain how to roughly explain how to obtain this universal family. So first of all, what is the family of marked K3 surface? So PP. So this is a smooth, proper map as usual, such that all fibers are K3 surfaces, but we want to have marking. And what is marking? Marking is of a family is an isomorphism of the corresponding local system with trivial local system with fiber, our favorite lattice. Okay, so phi is a trivialization of local system R2. So let me recall that before we suppose that B is simply connected, so we obtain a trivialization automatically. And here we just, for families of merged K3 surface, we ask this isomorphism to exist just from, this is our supposition. Okay? For a family of merged K3 surface, we can define, guess what? What map? If we have a, if we fixed this trivialization, what we can define for family of merged K3 surface?
Map to the modular space.
To what? No. As before. What we defined for a simply connected base before. We can define the period map, right? If we fix this trivialization, then we can define the corresponding period map. A period map. In the period domain. That is point to point here. We associate the image of the complexified H2 так, вроде нормально. H20 XB. Here. Okay, so if we fix a trivialization, we can define the corresponding period map, even if B is not simply connected. Okay, and now let me explain how to obtain a universal family FK3 over this modular space of merged K3 surface. We just glue the universal families of all K3 surface. And of course, we will obtain a universal family with marking. So this is trivialization if K3 of the corresponding local system if we have a universal family, of course, on this universal family of merged K3 surface, we will have this trivialization, right? And to obtain it, we, roughly speaking, just glue the corresponding universal deformations, and I will not. And here we use that there are no automorphisms of merged K3 surface, because otherwise we will not be able to glue them. And in the end of the lecture, I will explain. I will try to explain why we cannot glue them if we have automorphism. But if we don't have automorphism, we can glue and obtain something with trivialization. Okay, this is a difficult theorem. I don't have time. Maybe not difficult. It's a very simple idea, but it's quite technical. So I want to explain all the details. The only important thing to remember here is that if we don't have automorphisms, then we can obtain a fine modular space. We can hope to obtain a fine modular space, and if we have, we usually don't have fine modular space. And now let me formulate the statement and then to define global period map. Guess what will be global period map? Before we had local period map just for this base of deformations, and what will be global period map? So as I explained, if we have a trivialization of the corresponding of local systems, then we can always define period map, and the corresponding global period map will be the corresponding period map to fine modular space of merged K3 surface. So we have a trivialization, so we can define the corresponding period map, and this is so-called global period map for K3 surface. Global because it is defined on the whole modular space. Okay? Theorem. А сколько времени? For 38? Нормально. For merged K3 surfaces, there exists a fine modular space so there exists a universal family as K3 to N3 with trivialization попытаться новый маркер. О, зелененький. Не, лучше не стоило. Красный. Во. Так. So this means that for any family of merged K3 surfaces, there exists a map to this universal family such that the corresponding family of merged K3 surface is a pullback of the universal one. So I want to say that it's a very strong statement, the existence of such a universal family, right? So all families we can obtain as a pullback. So there exists this map and it's unique. Such that this is isomorphic to and K3. But there is a small problem that this fine modulus space is a 20-dimensional complex manifold. But the problem is that it's not Hausdorff. So it's not separated. We cannot separate some points. I will not explain why, but it is. It isn't Hausdorff. Okay? I will not explain why, because we just don't have time, but I want to say that it's very nice that we have such a universal family, but it's not smooth. It's not even Hausdorff, so we can't separate some K3 surface. And now let me explain what is global period map.
Excuse me, what then do you mean by complex manifold? What is complex manifold?
No, okay, ладно, maybe it's not, because we defined manifold as smooth, some complex space. Some complex space, but it's not Hausdorff, it's very, very bad. Okay, and now let me say something about global period map. Global period map. This is the corresponding to this universal family map from its base to the period domain. And theorem global Tarelli theorem tells you that this map is surjective. And in fact, this is a very difficult theorem. Unfortunately, I don't have time to explain why it's so, but let me just say what does it mean to be surjective in this case. This means that if we have a line in the period domain, so this means that self-intersection is 0 and intersection with its conjugated is greater than 0, then there exists a K3 surface with marking H2 as such that the image of complexified H20 of S is the corresponding line. So to any line in a period domain, there exists a K3 surface with marking with fixed isomorphism such that the image of the H20 part is this line. This is surjectivity statement. And in fact, also let me say that this map is étale in the sense that the corresponding differentials are isomorphisms, but not that we cannot hope that this corresponding global period map cannot be injective. Just because this is some smooth locus in 20-dimensional complex space, and this is something not Hausdorff. So we cannot hope that this is injective map. But what we will have in this case, in fact, is that it's not even injective on a connected component of this moduli space. But the statement is that if we throughout a countable unit of closed subset in the, from a connected component of this moduli space, then on this open subset, the corresponding global period map will be injective. So it's generically injective. So it's generically injective. So it's injective in a general point of this moduli space. But it cannot be injective just because this is not it's not separated. Okay. Okay, and it's surjective. And what next? Okay. Let me formulate something about some statements about Picard group of K3 surfaces. So let me first formulate corollary. That a very general point of this moduli space of marked K3 surface corresponds to the K3 surface of Picard rank 0. So in particular, it's not projective. It is not projective. So I will explain in a minute what means a very general. In fact, the same thing as before. If we throw out a countable union of some closed subsets, then on the corresponding open subset that we will obtain, all K3 surfaces will have Picard rank 0. Okay?
What's the difference between general point and very general point?
I think that сейчас скажу. So when we say general point, we first of all we usually assume that we talk about something connected, right? So we take a connected component, take a general point there, and here we don't assume that something is connected. It can have several connected components, but we mean that there are some fixed countable union, so some countable union of closed subsets. So we fix this countable union, and outside of them, so we say that there is some bad locus, and this bad locus is more or less. And for general point, it's a scheme theoretic notion, I think, general point of a scheme. Okay. So now proof. Suppose that we have a K3 surface with marking is marked K3 surface. Then from Lefschetz 1-1 theorem we know that its Picard group is isomorphic to the intersection of its second cohomologies with integer coefficients and H11 part of S. So we have that, so from this we obtain that Picard group is an intersection of integer cohomologies with orthogonal to H20 part, and this is, using our marking, this is an intersection of lattice with orthogonal to H20 with the image under the marking of H20 part, and this is intersection of the image of the corresponding global period map of this point. So from this we see that Picard group is non-zero if and only if there exists a point, non-zero point, in our lattice such that the image of the global period map lies in its orthogonal. Okay? And so from this we deduce that if this image, okay, I will write it somewhere. So if this image is a point of D, and we throw out a countable union of orthogonals, this is points of K3 of the corresponding lattice without zero, and this is countable set of hyperplanes. Then we have that Picard group of S is zero. So here we see what is an example of very general. So what we use here? First of all, we use that the global period map is surjective. So if we throw out this countable set of hyperplanes, we will obtain something open, and we know that for all this open, for all points on this open set, there exists a K3 surface that with the property that image of the corresponding global period map is this point, right? So we can construct such a K3 surface. And what we claim is that Picard group is non-zero if and only if the image lies in this union of orthogonals to all points in the corresponding lattice, right? And lattice is something Z model, so it's discrete. Okay, and so this is some countable set of hyperplanes. Okay, and outside this countable union, K3 surface have zero Picard group. So a very general K3 surface is not projective. Okay, so this is the first corollary, and maybe I don't have time to explain the following theorem. And in fact, it's so I need to say that in the theory of K3 surface, of course, a very important role plays lattice theory. There are a lot of Nikulin results about general lattices, and ну правда, что ты смеешься? And in fact, to prove this theorem, we need some of the results, some of the existence results of Nikulin. So, what's this theorem? Suppose that как бы ее обозначить? Ну ладно. Как обозначить решетку? L. L is a lattice of signature one, rho minus one, where rho is greater or equal to 1 and less or equal to 0, then there exists a K3 surface S such that its Picard group and this lattice are isomorphic. So if we take a lattice with a signature with this property, then there exists a K3 surface with this lattice. A very strong statement, right? And it, in fact, it uses both global Terrelli theorem and Nikulin's result about lattices, about the existence of some lattices. Okay. А сколько времени? And let me now explain very, very roughly why we can't hope why we can't construct a universal family of K3 surfaces without markings.
Что это курс сигнатуры решетки?
А?
Сигнатура решетки.
Ну да, сигнатура. Ну вот здесь такое предположение, что это сколько положительных и сколько отрицательных сами пересечений. У тебя, ну, у тебя решетка — это модуль с симметрической билинейной формой. Вот ты смотришь сигнатуру, соответствующей симметрической билинейной форме. Продолжаем семинар по алгебре у второкурсника. Так. Нет, решетка — это... Okay, lattice is not just that model, it's that model with symmetric bilinear form.
То есть мы как структура формы.
Ну да. И вот все эти результаты Никулина, они про существование, у тебя не просто как бы априори, ну z-модуль, тебе важно, как у тебя пересекаться будут между собой.
The one with the number of positives, first the number of positives.
Yes.
And negative.
Yes. Так. And now, okay, I think that next time we will discuss automorphisms of K3 surface, but first of all, let me say some comments about automorphisms and deformations. So suppose we have a smooth smooth compact connected variety, smooth connected variety, and suppose we have a smooth universal deformation of this variety, that is, we have the following vanishing of global sections. So we have this vanishing, then we have a universal family. Universal deformation of X. And now suppose that we have an automorphism of X. Morphism. Then what we will have? Then we have, roughly speaking, then we will have if we have an automorphism of a central fiber of the corresponding deformation, universal deformation, then we will obtain an automorphism of its base locally. So we росток, как сказать росток? Then we will have an automorphism of germ of B0. So 0 is the distinguished point over which we have our X. And also we will have an automorphism of the corresponding deformations. I will not explain why, I will just formulate the statement. So then there exists an open neighborhood. Как пишется neighborhood? Ладно, не важно. B of 0 and an open holomorphic embedding. Holomorphic embedding gamma B0 to be universal 0, and a commutative diagram universal B here is a small gamma and here is a big gamma, and commutative diagram, this commutative diagram, where sigma induces the automorphism that we had before of the central fiber, and for all B in this open neighborhood we have an automorphism of the fiber and its image. So roughly speaking, phi is an automorphism of the germ B universal in the point 0, and gamma is an automorphism of the germ of the corresponding universal family. Okay, so I'm not going to explain why this is so. It will follow from the universal property of B, but it's difficult to explain in a complex setting. But more or less, what is the statement? That if we have an automorphism, then we can deform it in a universal deformation. Okay, so there exists an open embedding such that and automorphism sigma such that sigma induce our fixed automorphism on the central fiber, and such that it induce an automorphisms of all nearby cycles. Okay. And this is always true when we have a universal deformation. And now what we will have for K3 surface? Why there is no moduli space, fine moduli space of K3 surface? So suppose we have a K3 surface, K3 surface, and suppose we have an automorphism of S that acts non-trivially on H1 STS. So why these automorphisms exist? Just because, so first of all, we have for a K3 surface isomorphism of its tangent bundle and its cotangent bundle, right? And this is one part. So it's enough to find an automorphism, find a K3 surface, an automorphism of K3 surface that acts non-trivially on its Picard group. Because Picard group lives here, right? And if you find an automorphism of K3 surface that acts non-trivially on its Picard group, then we are done. For example, we can consider a K3 surface that is an intersection of two divisors of B degree 1, 1. Intersection of divisors of B degree 1, 1 and 2, 2. Then we have two projections from K3 surface to one copies of P2 and to second copies of P2, and this is double covering. And if we have a double covering, we have the corresponding involution. And an exercise, you try to compute how these two involutions, sigma 1 and sigma 2, acts on the Picard group of S. The Picard group will be of rank 2. Okay, try to compute how these involutions acts on Picard group, and if it will act non-trivially, then if it acts non-trivially on the Picard group, of course it will act non-trivially here, and this is an isomorphism from third duality. Okay, so maybe next time we will discuss more examples of automorphisms of K3 surface, but the statement here is that there exists K3 surface with automorphisms that acts non-trivially on their first cohomology groups. Okay? And now how we can construct and now, why we don't have moduli space of K3 surface? So for a K3 surface S, we can consider the corresponding universal deformation of S, F universal. And we have already discussed that there is an open holomorphic embedding and the corresponding local automorphisms sigma small and sigma big, so that universal and such that the restriction of this automorphism is sigma. And we know that, in fact, this pair is uniquely determined by the corresponding tangent map, by the corresponding tangent map at 0, and this is from Kadeira-Spencer map. It's just the induced non-trivial induced by sigma automorphism of the first cohomologies. And this is from the Kadeira-Spencer map that we discussed last time. Okay, and now suppose that there exists Мне кажется, это уже похоже на какую-то картину современного художника. Вот это близко. Thank you. А где маркер? Да, здесь, спасибо. Пора, мне кажется, поменять цвет на какой-нибудь более сдержанный. О, отлично. Окей. And now we suppose that there exists a fine moduli space, a fine moduli space for K3 surface without marking, just for K3 surface. So suppose that there exists a universal family over some moduli space. Then we know that there should exist a map from deformation of S to this moduli space such that S is a pullback from this universal family. But what we have using this automorphism, but for all points in U, fiber of SU and gamma SU are isomorphic. Isomorphic. Automorphism sigma. So, if this map, if we will denote this map by G, we should have G at U should be the image of U should be the same as the image of gamma U. And this means that our map from deformation of S to the universal family should be factorized through the action of gamma. Right? And hence we should obtain that this family NS is the inverse image of a family over deformations of S where we identified points of gamma. But also what we have that this gamma induce an automorphism, not as before automorphism of a germ, but a real automorphism gamma of the universal family such that we have exactly the same commutative diagram but for a real automorphism. And here we should have that automorphism that is restriction of gamma to the central fiber is an automorphism of S that acts on its first cohomologies as sigma, as the tangent map to gamma as sigma, and we know that this is a non-trivial automorphism, and so from this we obtain that the corresponding family over this factorization, so fiber over 0 is S factorization. We factorize S by the action of sigma prime, but it is not a K3 surface. It is not a K3 surface, and so we cannot. So it is not inverse image K3 and K3. Okay, so a very rough idea is that suppose we have a fine modular space for all K3 surface, then all universal deformations should be a pullback from this family. But if we have a non-trivial automorphism of on S that acts non-trivially on its first cohomologous group, then we can consider the corresponding automorphism of this deformation, and we see that if we have this map should identify points of these automorphisms. And more or less we can't have these identifications. Or I don't know, maybe another way to explain the same idea that of course we can have isotrivial families of K3 surface, and suppose we have a non-trivial automorphism, then we can скрутить. Then we can twist this isotrivial family using this automorphism, and so the corresponding isotrivial family should give you the same point of MK3, but if we twist it by an automorphism, then this is a contradiction, because the corresponding family is non-trivial. Okay? So that's the problem. But okay, maybe the only one thing that you should remember that if you have an automorphism, you can't hope to have universal family. Окей? Все, можно выключать. Как выключать? Вопрос. Нет, я не буду это делать сейчас. Не надо, то оно все светит. А как выключить? Привет. Я бы боялась там нажимать, извини.
Ну там, да. Ну я выключу.
Вот, на, держи.
Спасибо.